Imagine that late one night, a voice comes to you in your loneliest hour and says, "This life, exactly as you are living it now, you will live again. Not something like it. This. Every breath, every sorrow, every forgotten thought, returning in the same order, without end." For most of history, that was a nightmare for poets. Then, in 1890, a French mathematician proved something close to it as a theorem. The claim is not mystical, it is arithmetic. Take any system that is closed, that has a finite number of possible arrangements, and that runs for unlimited time. That system must, eventually, return arbitrarily close to the exact state it began in, and then do it again, forever. The configuration of particles that is your body and your memory at this instant would, given enough time, reassemble. You have been here before, you will be here again. This is the Poincaré Recurrence theorem, and applied to a cyclic universe, one that expands, collapses, and is reborn without end, it stops being mathematics and becomes a verdict on your own existence. By the end, you will understand what the theorem demands, how cyclic models of the cosmos, from colliding membranes to Penrose's endless Aeons, try to supply the eternity it needs, and why the recurrence time is so vast the age of the universe rounds to zero beside it. And you will face the question beneath the physics. If a copy of you returns, remembering nothing, is it truly you or a stranger wearing your life? If you find value in explorations like this, in following the puzzles that keep physicists awake at night, consider subscribing. It helps these deep dives reach more curious minds. Now, let us begin. There is a particular kind of dread that does not come from the dark. It comes from the light. It comes from understanding something precisely, following an argument step by step, agreeing with each step, and arriving somewhere you did not want to go. The Poincaré Recurrence theorem is one of those arguments. To feel its weight, we have to begin not with the cosmos, but with a single closed room, and the question of what a finite world is permitted to do with infinite time. Let us start with the man and the mistake. Henri Poincaré was, at the close of the 19th century, perhaps the last person alive who understood all of mathematics at once. In 1885, King Oscar II of Sweden announced a prize competition to honor his 60th birthday. One of the questions was old and simple to state and brutal to answer. Is the solar system stable? Will the planets keep their orbits forever, or will they one day drift, collide, or fall into the sun? This is the n-body problem, and Poincaré attacked it with everything he had. He won the prize in 1889, and then, as the winning memoir was being typeset for publication, an editor named Lars Edvard Fragmen pressed him on a passage that did not quite hold. Poincaré looked again. He had made an error. He had assumed a kind of orderliness in the orbits that was not there. In correcting it, he discovered something that would not have a proper name for almost a century: deterministic chaos. The fact that perfectly lawful systems can be so sensitive to their starting conditions that their long-term future becomes, in practice, unpredictable. He paid out of his own pocket to have the flawed, already printed edition recalled and destroyed. The cost, by most accounts, exceeded the prize money he had won. What does it mean that the recurrence theorem was born from a correction to a mistake about whether the heavens are stable? It means that from the very first, this idea lived at the boundary between order and disorder, between a cosmos that repeats and a cosmos that wanders. Out of that correction, in the published memoir of 1890, came the theorem that concerns us. To state it, we need one idea: phase space. Picture a single particle. To describe it completely at an instant, you need to know where it is and how it is moving, its position and its momentum. Write those numbers down, and you have specified a single point in an abstract space of all possible states. Now do that for every particle in a system at once. The entire state of a box of gas, with its countless molecules, collapses into a single point in an enormous high-dimensional space. As the gas evolves, as the molecules collide and scatter, that single point traces a path through phase space. The whole history of the system is one curve through this space of all the ways it could be. Think of it this way. Picture a vast library in which every possible arrangement of a system has its own shelf, its own exact address. The system's history is a librarian walking the aisles, visiting one address after another. The question Poincaré asked was deceptively plain. If the librarian walks forever, and the library, though immense, is finite, must the librarian eventually return to a shelf already visited? Must the walk come home? His answer was yes, with conditions. The theorem states that for a system whose phase space has a finite total volume and whose evolution preserves that volume, almost every state will, after a sufficiently long time, return arbitrarily close to where it began. Not approximately near, as close as you care to demand. And having returned once, it must return again and again, infinitely often. The librarian, walking a finite library forever, not only revisits old shelves, the librarian revisits every shelf an unlimited number of times. Notice the three conditions, because everything that follows in this investigation will turn on them, and in the final part, we will return to each one with a harder eye. First, the phase space must be finite, bounded. The system cannot leak away to infinity. Physically, this is secured by a wall and by the conservation of energy, which confines the motion to a finite shell of possibilities. Second, the evolution must preserve phase space volume. This is guaranteed for the frictionless fundamental laws of mechanics by a result called Liouville's theorem, which we will come to. Third, and this is the quiet clause, the return is to almost every state, and it is arbitrarily close, not perfectly identical. A vanishingly small set of special states may never return at all. Keep that clause in mind. We will need it. Let us make the second condition concrete, because it is the engine of the whole result. Liouville's theorem, named for the mathematician Joseph Liouville, who wrote down its underlying form in 1838, says that as a system evolves, the volume it occupies in phase space does not shrink and does not grow. Picture phase space filled with an incompressible fluid. You can stir it, stretch it into long, thin filaments, fold it back on itself endlessly, but you can never compress it into a smaller total volume, and you can never make it expand. The fluid is conserved. And because the fluid cannot thin out and spread into ever new regions without limit, it is forced, eventually, to fold back over places it has already been. Recurrence is the shadow that this incompressibility casts across infinite time. There is a hidden assumption worth dragging into the light, because it will matter at the end. For the theorem to force the system back near any particular state, the system must actually wander through the accessible region of its phase space, rather than getting trapped in some small corner of it. Boltzmann gave this assumption a name in the 1870s, the Ergodic hypothesis, the idea that over enough time, a system visits, or comes arbitrarily close to, every state available to it at its energy. It is a beautiful idea, and for many systems it is approximately true. But it is not a free gift. In the 1950s and 60s, the mathematicians Andrei Kolmogorov, Vladimir Arnold, and Jürgen Moser proved a result now called the KAM theorem, which showed that a great many real systems are not fully ergodic at all. Islands of stable, regular motion survive amid the chaos, and a trajectory caught on one of those islands is confined to it, forever barred from vast tracts of phase space it will never enter. Recurrence holds within the region a system actually explores. Whether a given system, let alone the entire universe, explores all of its possibilities, or only a sliver of them, the theorem does not say. It is an extra assumption, quietly required, and we will watch it strain. Here, a fair observer should pause and ask the obvious question. If everything returns, why does the world look so relentlessly one-directional? Cream stirred into coffee never unstirs. A shattered cup never leaps back onto the table whole. Heat flows from hot to cold, and never the reverse. This is the second law of thermodynamics, the increase of entropy, the arrow of time. How can a theorem that promises eternal return live in the same universe as a law that promises eternal decay? This exact collision happened, and it happened as one of the great scientific quarrels of the 19th century. On one side stood Ludwig Boltzmann, who had built the bridge between the invisible jostling of atoms and the measurable quantity we call entropy. His relation, later carved on his tombstone in Vienna in the compact form written by Max Planck, reads S equals K log W. Entropy, S, equals a constant, K, times the logarithm of W, the number of microscopic arrangements that produce the same large-scale appearance. A tidy, low-entropy state has few arrangements. A disordered, high-entropy state has overwhelmingly many. Systems drift toward disorder for the most boring of reasons. There are simply vastly more ways to be disordered than to be ordered. On the other side stood a young mathematician named Ernst Zermelo, then assistant to Planck. In 1896, Zermelo turned Poincaré's own theorem into a weapon. If a closed system of gas must eventually return arbitrarily close to its initial state, then its entropy must also return arbitrarily close to its initial value. Entropy cannot climb forever. It must eventually come back down. Therefore, Zermelo argued, the second law and the atomic theory of gases cannot both be literally and universally true. One of them must give. Boltzmann's reply was sharp, and it conceded more than it first appeared. He did not deny recurrence, he accepted it. The system will return, he said. But ask how long you would have to wait. For a quantity of gas no larger than a cubic centimeter, Boltzmann estimated the recurrence time at around 10 to the power of 10 to the power of 19 seconds. That is not 10 followed by 19 zeros, it is 10 followed by a number of zeros that is itself 10 billion billion. Written out, the number of digits would not fit inside the observable universe. The recurrence is real, Boltzmann said, and it is also, for any practical purpose, never. What does it mean that the second law is not a law of certainty, but a law of overwhelming probability? Boltzmann said it plainly in 1895. His theorem and the second law itself were, in his words, only theorems of probability. Entropy almost always increases. Over any human span, over any cosmic span we will ever witness, it increases with a reliability indistinguishable from certainty. But buried in the mathematics is an admission. The arrow of time is not stamped into the fundamental laws. The microscopic equations run equally well forwards and backwards. The arrow comes from somewhere else, from the fact that the universe began in a state of extraordinarily low entropy and has been climbing ever since. We will return to that beginning and to the question of what could have set it, because it is the hinge on which this entire story finally turns. For now, hold the picture clearly. A finite, closed, energy-conserving system, left alone for unlimited time, must return. Its entropy must eventually dip back toward where it started, however astronomically rare such a dip may be. The recurrence is not a loophole or a paradox, it is a theorem. The only thing standing between us and eternal return is time, and the question of whether the universe has enough of it, and whether the universe is the kind of closed, finite box the theorem requires. Those two questions, time and the box, are where we turn next. Because to make the theorem speak about you, and not merely about a cubic centimeter of gas, we need a cosmos that lasts forever and closes back on itself. We need a cyclic universe. The Poincaré recurrence theorem on its own is a statement about a box. To make it a statement about a life, we have to enlarge the box until it becomes the cosmos, and we have to find the cosmos a supply of time without end. Both of those steps take us out of clean mathematics and into the contested frontier of cosmology. Let us proceed carefully, presenting each model as its proponents present it, and noting, without yet judging, where each one strains. Begin with the oldest version of the idea, the cyclic universe. The intuition is ancient. The Stoic philosophers of Athens taught ekpyrosis, a periodic conflagration in which the entire cosmos is consumed by fire and then reborn, identical to live its history again. The same word, ekpyrosis, out of the fire, will return in a moment attached to a modern theory in string physics. The intuition that the cosmos breathes, expanding and collapsing without beginning or end, is one of the most natural ideas a human being has ever had. The difficulty has always been making it survive contact with physics. Long before the physics, the idea had a prophet. In the summer of 1881, walking beside a lake in the Swiss Alps, near a great pyramidal rock, the philosopher Friedrich Nietzsche was seized by a thought he would call the heaviest weight. He imagined a demon stealing into one's loneliest loneliness to whisper that this life must be lived again and again, innumerable times, with nothing new in it, every pain and every joy returning in the same sequence, even this very moment. And the demon's whisper itself, and the spider in the moonlight between the trees. The eternal hourglass of existence, the demon says, is turned over again and again, and you with it, a speck of dust. Nietzsche did not offer this as cosmology. He offered it as a test. Could you bear it? Could you so affirm your life exactly as it is that you would will its infinite repetition rather than be crushed by the thought? In his private notebooks, he even sketched a quasi-physical argument for it. A finite quantity of energy, a finite number of configurations, and infinite time must, he reasoned, replay every arrangement without end. He never published the proof, and physicists regard it as more intuition than demonstration. But notice that his intuition has exactly the shape of the theorem we have just met. Finite states, unlimited time, inevitable return. And Nietzsche was not the first. The Stoic philosophers of ancient Athens had taught it more than 2,000 years earlier, that the cosmos passes through a great year, is consumed in a universal fire, and is reborn to live its identical history again. The same Socrates teaching in the same marketplace, every event recurring down to the smallest gesture. The Pythagoreans before them said much the same. What is striking is the difference in mood. For the Stoics, the recurrence was governed by a rational, divine ordering principle, a cosmic reason that wills each identical world into being. The return was the signature of providence, not of accident. The modern version keeps the machinery and strips away the providence, and in doing so, it changes the recurrence from a sign of cosmic reason into a sentence of cosmic indifference. That shift from a cosmos that repeats because it is governed to a cosmos that repeats because it is blind is worth holding on to. Before we are finished, we will ask which of those two pictures the evidence actually supports. The first serious attempt to build the cyclic cosmos as physics came from the American physicist Richard Tolman in the 1930s. Tolman took seriously the idea of a closed universe that expands, slows, halts, recollapses to a fiery crush, and bounces into a new expansion over and over. He then did something his predecessors had not. He applied the second law of thermodynamics to the cycles themselves. and he found a problem that has haunted every cyclic model since. Entropy increases. Each cycle generates disorder, radiation, the burnt residue of stars and structure. And the second law forbids that residue from ever being cleaned away. So the entropy carries over from one cycle into the next. And a cycle carrying more entropy is larger and longer than the one before it. Run the cycles forward, and they grow without bound. But here is the sting. Run them backward, and they shrink. Each earlier cycle was smaller and shorter than the one after. Follow that shrinking sequence into the past, and it converges. It points toward a first cycle, a smallest cycle, a beginning. The model built to abolish the origin instead implied one. What does it mean that the very first rigorous cyclic universe, the one designed to let the cosmos run eternally, turned out to point back to a starting line? Tolman himself, it should be said fairly, did not draw that conclusion. He preferred to imagine the cycles extending, as he wrote, from minus infinity in the past to plus infinity in the future. The inference that the entropy buildup forces a beginning came later, from other cosmologists looking at his own mathematics. Hold that tension. The eternal model that secretly requires a beginning is a pattern we will see repeat, and in the final part it will become the center of the case. Modern cosmology has produced more sophisticated attempts to defeat Tolman's entropy problem. The most discussed comes from the physicists Paul Steinhardt and Neil Turok, and it is built from the strange machinery of string theory. In their ekpyrotic model, proposed in 2001, and its cyclic extension proposed in 2002, our entire three-dimensional universe is a membrane, a brain, floating in a higher dimensional space. Parallel to it, across a tiny gap in an extra dimension, floats another brain. The two brains are drawn together, and when they collide, the energy of the collision is the event we call the hot Big Bang. There was no singular beginning of space and time. There was a collision, and before it, another universe. The model is called ekpyrotic precisely because of that Stoic word, out of the fire, and it claims to solve Tolman's problem with an elegant move. In each cycle, after the stars burn out, a phase of accelerated expansion, driven by what we observe today as dark energy, stretches the universe enormously, diluting all the accumulated matter and radiation and entropy until space is nearly empty and nearly perfectly smooth. The brains then draw back together, collide again, and the cycle restarts from a clean, low-density slate. The essential trick is that the brains themselves expand a little more each cycle. The total volume grows, so the entropy density, the disorder per unit volume, can reset, even as the raw total of entropy is pushed outward and diluted into ever larger space. The cycles need not grow longer. They can repeat, in principle, forever, into the past and into the future. Steinhardt and Turok titled their popular account of it plainly, Endless Universe. The model makes a sharp, falsifiable prediction, and, to its credit, this is a scientific virtue. Where the standard inflationary picture of the early universe predicts a particular spectrum of primordial gravitational waves rippling the cosmic background, The ekpyrotic mechanism predicts essentially none at those scales. A clear detection of those primordial waves would falsify it. The absence of such a detection so far is something Steinhardt now points to, having become one of inflation's most prominent critics. We will return, in the final part, to a debate Steinhardt himself has provoked about whether the rival theory of inflation is even testable at all. The second great modern attempt belongs to Roger Penrose, the mathematical physicist who shared the 2020 Nobel Prize for proving that black holes are an inevitable consequence of general relativity. His model is called conformal cyclic cosmology, and it is the strangest of them all. Penrose proposes that the universe consists of an infinite sequence of what he calls Aeons, and the trick that joins them is geometric, almost poetic. Consider the far, far future of our own Aeon. Every star has burned out. Every black hole has evaporated. What remains is an empty, expanding void, filled only with massless radiation, photons drifting through endless dark. Now, Penrose observes, a universe of only massless particles has lost track of scale. Massless particles travel at the speed of light and do not experience time or distance in the ordinary way. Such a universe cannot tell the difference between unimaginably vast and unimaginably small. And so, mathematically, through an operation called conformal rescaling, the cold, infinite, empty future of one Aeon can be smoothly glued to the hot, dense, compact Big Bang of the next. The end becomes the beginning. There is no contraction, no crush, no bounce. There is only the geometric identification of an ending with a beginning, repeated without end. The price of this elegance is steep, and Penrose is candid about it. For the rescaling to work, the far future must contain no rest mass at all. Everything must become massless. This requires that all massive particles eventually decay, including, controversially, the proton, whose decay has never been observed despite decades of searching, and even, in the deepest future, the electron, for whose decay there is no accepted theory whatsoever. This is the most criticized assumption in Penrose's framework, and it is fair to flag that it rests on physics we have never seen. Underneath conformal cyclic cosmology lies an older and deeper idea of Penrose's, one we must hold on to because it will matter enormously at the end. In 1979, Penrose proposed what he called the Weyl curvature hypothesis. It addresses the deepest puzzle in all of cosmology. Why did the universe begin in such an extraordinarily ordered, low-entropy state? Penrose's answer was geometric. The part of space-time curvature that describes free gravitational distortion, the Weyl curvature, was very nearly zero at the Big Bang, meaning the early universe was almost perfectly smooth and uniform. This smoothness is the low gravitational entropy that gives the arrow of time its direction. Conformal cyclic cosmology is, in part, Penrose's attempt to explain why each new Aeon inherits that pristine, smooth, low-entropy beginning. Keep that question burning. Why is the beginning so precisely, so improbably ordered? We will not be able to avoid it. Penrose has even claimed observational support. He and his collaborators argue that gravitational signals from black holes in the previous eon should leave faint circular marks in our cosmic microwave background, concentric rings of unusually low temperature variation. And in 2018, signals they named Hawking points, the entire evaporated output of supermassive black holes from a prior eon, concentrated into small, warm patches. We will examine in due course how that claimed evidence has fared under independent scrutiny. For now, note only that here is a cyclic model bold enough to make predictions about the sky. There are others. Loop quantum cosmology replaces the singular Big Bang with a big bounce, a moment when, at the unimaginable densities of the Planck scale, gravity itself turns repulsive, and a collapsing prior universe rebounds into expansion rather than crushing to a point. The Baum and Frampton model invokes an exotic form of dark energy and a turnaround a fraction of a second before the universe would tear itself apart, keeping a single, nearly empty patch with almost no entropy to seed the next cycle. Each model is a different piece of engineering aimed at the same target, a cosmos that runs forever, supplying the unlimited time the recurrence theorem demands. Before we weigh whether any of these models can truly deliver eternity, it is worth pausing on what eternity would actually contain. If the universe simply keeps expanding, as the evidence currently suggests, then the far future is not a fiery collapse, but a long, slow fade. And the physicists Fred Adams and Gregory Laughlin mapped its stages in detail in 1997. We live now in what they call the stelliferous era, the age of stars, a brief and brilliant window in cosmic history. It will not last. Star formation will sputter out within a few tens of trillions of years, as the gas needed to forge new suns runs thin. The last and smallest red dwarfs, misers that burn their fuel slowly, will gutter out somewhere around 100 trillion years from now. The sky will go dark and stay dark. Then comes the degenerate era, a universe lit only by the cooling embers of dead stars, white dwarfs and neutron stars, and the cold cinders of failed suns drifting in deepening blackness. If the proton itself decays, as some theories predict, and as experiments like the Super Kamiokande detector in Japan have searched for, so far without success, then even this dead matter will slowly evaporate over a span of perhaps 10 to the 37th years, until the baryons that make up every familiar thing are gone. The black hole era follows, an almost unthinkable stretch in which black holes are the only significant structures left, slowly bleeding their mass away through the faint glow of Hawking radiation. The largest of them, the supermassive giants that once anchored galaxies, will take on the order of 10 to the 100th power years to evaporate completely. And then the dark era, a cold, thin, nearly empty sea of stray photons and isolated particles, drifting through a space that expands forever toward a temperature approaching absolute zero. Even then, the silence is not perfect. A universe ruled by dark energy has a horizon, and that horizon radiates a faint thermal whisper, the Gibbons-Hawking temperature, around 10 to the negative 30th of a degree above absolute zero. This is the heat death, the maximum entropy end state, the still and frozen ocean toward which our universe, left to itself, is sailing. It is against this backdrop that the recurrence claim becomes most vivid and most terrible. For if the universe could somehow run beyond even this frozen end, the recurrence theorist says, then out of that equilibrium void, given conditions we will scrutinize later, the configuration could, in principle, scramble itself back toward order, and the whole show could begin again. Whether that is genuinely possible, and what it quietly assumes, is exactly what the final part of this investigation must test. And there is a second route to unlimited time and unlimited boxes, one that does not require cycles at all: the multiverse. Here we encounter the second of our key concepts. The theory of eternal inflation, developed in the early 1980s by Alan Guth, Andre Linde, Paul Steinhardt and Alexander Vilenkin, proposes that the rapid expansion of the very early universe never fully stops. In some regions it continues, and within that endlessly inflating background, pocket universes, bubbles, continually nucleate, each one a self-contained cosmos. The proponents argue this produces an unbounded number of universes, and, within our own, an unbounded number of regions the size of our observable horizon. The physicist Max Tegmark has organized these ideas into a four-level hierarchy, from regions simply beyond our cosmic horizon to bubbles with different physical constants, to the parallel branches of quantum mechanics, to the most speculative level of all, in which every self-consistent mathematical structure is held to be a real universe. Why does the multiverse matter for recurrence? Because it offers exactly the two ingredients the theorem needs. It offers unlimited time through endless inflation, and it offers an unlimited number of finite boxes, each pocket universe or each horizon-sized volume serving as its own bounded system. And in an infinite expanse of such boxes, every possible arrangement of matter that can occur must occur and must recur. Tegmark has spelled out the consequence at the most personal level. In an infinite, uniform space, he calculates, there should be an identical copy of you reading these very words at a distance of around 10 to the power of 10 to the power of 29 meters of 10 to the power of 29 meters. Not similar, identical. Built from the same arrangement of particles with the same memories, making the same choice you are making now. This is where the abstract theorem becomes a blade pointed at the self. So let us look directly at the number that governs it, the recurrence time, because its sheer size is part of the argument and part of the dread. Recall Boltzmann's estimate for a single cubic centimetre of gas, 10 to the 10 to the 19 seconds. Now scale that up to the entire universe. The physicist Don Page performed this calculation for the quantum state of a region containing roughly the mass of the observable universe. His result is among the most extreme numbers ever written down by a working scientist. The recurrence time, he found, is approximately 10 to the power of 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 2.08. Sit with the structure of that number, because ordinary language fails it completely. 10 to the power of 2 is 100. 10 to the power of 100 is a googol, 1 followed by 100 zeros, already more than the number of atoms in the visible universe. 10 to the power of a googol is a googolplex, a number you could not write out even if every particle in the cosmos were an ink drop. And Page's number stacks yet another exponent on top of that. Each new 10 in the tower does not multiply the number, it re-exponentiates the entire tower beneath it. The count of digits in this number is itself a number with more digits than the universe could store. And here is the strangest feature, the one that makes the number feel almost like a taunt. It does not matter what units you measure it in. Seconds, years, the age of the universe, the lifetime of a proton. It makes no difference. The choice of unit changes only the smallest exponent at the very bottom of the tower, and that change is utterly swallowed. Page also estimated the recurrence time for a different inflationary scenario and produced an even taller tower. A number, he noted, may be the longest finite length of time ever explicitly calculated by a physicist. Against such a span, the 13.8 billion years since our Big Bang is not small. It is, mathematically, indistinguishable from zero. What does it mean that the return is guaranteed, and also that it would take longer than any number a human being can hold in the mind? It means the recurrence lives in a peculiar category of truth, certain and unobservable. It will happen, and it will never be seen to happen by anyone, ever. And yet, the cyclic and multiverse models insist time is not in short supply. If the cosmos is truly eternal, then even a number that tall is not a barrier. It is merely a waiting room. There is a further turn that deepens the strangeness. The theorem, as Poincaré proved it, was classical, about positions and momenta. But the world is quantum. Does recurrence survive the transition? In 1957, the physicists Paolo Bocchieri and Antonio Loinger proved a quantum version. For a closed quantum system whose energy levels are discrete, the quantum state will, after a finite time, return arbitrarily close to its initial state. The discreteness of the energy levels plays the role that the finite box played in the classical theorem. So yes, in the quantum world too, a closed, bounded system must return. But notice the condition: a discrete spectrum, a bounded system. A particle that is free to fly off to infinity has a continuous spectrum, and for it, recurrence fails. The wave packet simply spreads and disperses and never reassembles. This will matter. An expanding universe, racing apart faster and faster, looks far more like the particle that disperses than like the box that returns. We will return to that crack in the foundation. there is one more quantum subtlety, and it cuts to the very meaning of the word exact in our title. Quantum mechanics holds that identical particles are genuinely indistinguishable. Two electrons are not merely similar, there is no fact about which one is which. Swap any two electrons anywhere in the universe and you have not changed the physical state at all, because there was never a label to swap. What then does it mean to say that the same atoms return to the same arrangement? If the particles carry no individual identity, then a recurrence built from different electrons in the same configuration is not a copy of the original state. By the rules of quantum mechanics, it simply is that state. The recurrence is exact in a sense deeper than counting. And yet, by the same token, the very notion of your particular atoms returning begins to dissolve, because your atoms were never particularly yours to begin with. This brings us to the third of our key concepts, and to the question hiding beneath the physics. Is time an illusion? Because if it is, then recurrence is not even an event that happens in the future. It is a feature of a structure that simply is. In 1908, the mathematician Hermann Minkowski stood before an assembly in Cologne and declared that space by itself and time by itself were destined to fade into shadows, and that only a union of the two would endure. He had recast Einstein's relativity as a four-dimensional geometry, a single block of space-time in which past, present and future are all equally laid out, like the frames of a film that already exists in full. This is the block universe, the view philosophers call eternalism. In it, the flow of time, the sense of a moving now, is not a feature of physics, but a feature of our experience. Einstein himself, in a letter of condolence written in 1955 for his lifelong friend Michele Besso, weeks before his own death, wrote that, for those who believe in physics, the distinction between past, present and future is only a stubbornly persistent illusion. It is fair to note that this was a private letter of grief, not a technical paper, and that the English wording owes something to its translators. But the idea it gestures at is taken seriously in physics. It is taken so seriously that one of the deepest equations in the attempt to unite quantum mechanics with gravity, the Wheeler-DeWitt equation, written in the 1960s, contains no time variable at all. In it, the universe as a whole simply is, a single, timeless wave function, and the flow of time we experience must somehow emerge from within it. How that emergence works is, candidly, one of the great unsolved problems of physics. The physicist Julian Barber has pushed this to its limit, arguing in his book The End of Time that time does not exist at all, that reality is a vast, static collection of moments he calls Platonia, each instant complete in itself, the illusion of flow assembled by our minds from the records each moment contains. What does it mean that recurrence might not be a repetition in time, but a structure outside of it? If the block universe is real, then you do not live again after a Poincaré recurrence time. You simply are, eternally, statically. woven into the fabric of a four-dimensional whole, perhaps many times over. The terror and the comfort change shape. There is no second performance. There is only the one frozen real, and you fixed within it. And so we arrive at the question the whole subject was secretly about from the beginning. Suppose the cosmos is eternal. Suppose a configuration of particles identical to you down to the last electron reassembles, whether across the recurrence time of a cyclic universe or across the infinite expanse of a multiverse. Is that you? The philosopher Derek Parfit spent a career on this question. In his work Reasons and Persons, he imagined a teleporter that scans and destroys you here and builds an exact replica elsewhere. And he asked whether the replica is you or merely someone exactly like you. His unsettling conclusion was that identity, in the strict sense, may not be what matters, that what we call a person is just a pattern of physical and psychological continuity, with no further, deeper fact underneath. On that view, the recurring copy has as much claim to be you as you have to be the person who began watching this. On another view, the view that there is something more to a self than its arrangement, the copy is a stranger, and you die, and someone else, identical and unaware, lives your life again in your place. The physics cannot settle this. That is not a failure of the physics, it is a sign that we have reached its edge. And it is precisely at that edge, where the equations fall silent and the questions grow larger than any measurement, that we must change our posture. For the first part of this exploration, we have presented. We have laid out the theorem, the cyclic models, the multiverse, the numbers, the strange and beautiful machinery of an eternal cosmos, all as their proponents offer them. Now we must examine, because every one of these grand structures, the eternal cycles, the infinite time, the self that returns by chance, rests on assumptions. And it is time to test whether those assumptions can bear the weight that has been placed on them. For the past hour, the posture of this investigation has been that of a reporter. We have presented the recurrence theorem, the cyclic universes, the multiverse, the staggering numbers, the dissolving self, each as its advocates presented. We have agreed to nothing and denied nothing. That was deliberate. The strongest case is built by first granting an argument its best form. Now the posture changes. Now we cross-examine. We take each load-bearing assumption beneath the claim that you will live this exact life again, and we ask whether it can hold the weight. And we will find that the structure, examined honestly, does not collapse into eternal return. It collapses into something else entirely. Begin with the first condition of the theorem, the one we were told to keep in mind. Poincaré's proof requires a finite, bounded phase space. The system must be a closed box. The librarian can only be forced to return to old shelves if the library is finite and the doors are locked. Remove the walls, let the aisles extend without end, and the librarian may walk forever and never repeat a single address. So, we must ask the plain question: is the universe a closed box? The evidence of the last quarter century says, emphatically, no. In 1998, two teams of astronomers measuring distant supernovae discovered that the expansion of the universe is not slowing down as a closed, recollapsing cosmos would require, it is speeding up. A mysterious dark energy is driving galaxies apart at an accelerating rate, and every projection of that acceleration leads not to a fiery recollapse, not to a bounce, but to an ever emptier, ever colder, ever more dispersed void. Cosmologists call the end state the heat death, an approach to an empty space governed by dark energy alone, in which every galaxy beyond our local group is eventually carried past our horizon, never to be seen again. This is not the box the theorem requires. It is the opposite of the box. It is a system leaking its contents past a horizon faster and faster, forever. And recall the quantum version of recurrence, proven by Poincaré and Liouville. It works only for a system with a discrete spectrum, a bounded system. A system that disperses to infinity has a continuous spectrum, and for it, recurrence simply fails. The wave packet spreads and never returns. The accelerating universe we actually inhabit looks far more like the dispersing packet than the returning box. The standard model of cosmology, the one supported by the actual measurements, does not predict your return. It predicts your permanent dissolution into cold and dark. The proponents of recurrence know this, of course, and they have an answer. They point out that even an empty, accelerating de Sitter universe has a horizon, and that horizon has a finite entropy, which implies a finite number of accessible quantum states. A finite number of states, given infinite time, must eventually recur through random fluctuation. So the box, they say, sneaks back in through the horizon. This is clever. But notice what it has now become. The recurrence is no longer the orderly clockwork return of a closed mechanical cosmos. It is a thermal fluctuation, a spontaneous, random reassembly out of an equilibrium void. And the moment we say the word fluctuation, we have opened a door that the recurrence argument cannot close. We will walk through that door shortly, and what waits on the other side is fatal to the whole picture. Indeed, the physicists Dyson, Claiborne and Susskind, who first took de Sitter recurrence seriously, titled their 2002 study "The Trouble with de Sitter Space," and argued that such a universe may be unstable, decaying or destabilizing long before any orderly recurrence could complete, so that the very fluctuation invoked to rescue recurrence might never arrive at all. But first, the deeper problem, the supply of time itself. Every version of eternal return, the cyclic models and the multiverse alike, depends on one thing above all others. It depends on time being infinite. The cosmos must have run forever, or be able to run forever, for the recurrence to complete even once. So we must ask the second question, the one the cyclic models were invented to answer with a confident yes. Has the universe existed for infinite time? Can it? Here the prosecution calls its most powerful witness, and it is not a theologian. It is a theorem, proved by 3 cosmologists, none of them arguing for any religious conclusion. In 2003, Arvind Borde, Alan Guth, and Alexander Vilenkin published a result now known as the Borde-Guth-Vilenkin theorem. Its power lies in its generality. It makes no assumption about the specific contents of the universe, no assumption about the form of gravity, no assumption about exotic matter. It is, in their words, a simple kinematic argument. And it proves this. Any universe that has, on average, been expanding throughout its history cannot be infinite in the past. It must have a past boundary. It must have a beginning. Consider what this does to the cyclic models. They were built precisely to avoid a beginning, to let the cosmos cycle eternally backward in time. But a universe that expands more than it contracts on average over its history is caught by the theorem. And the cyclic models, with their net expansion each cycle, the very feature Steinhardt and Turok use to defeat the entropy problem, are exactly the kind of on-average expanding universe the theorem forbids from being past eternal. The escape from the entropy problem leads straight into the jaws of the boundary theorem. In 2012, Vilenkin, together with Audrey Mithani, examined the 3 leading strategies for an eternal past: cyclic evolution, an eternally inflating multiverse, and an emergent universe that sits statically before expanding. They concluded that none of them can be past eternal. The cyclic universe, Vilenkin wrote, cannot be past eternal. The static cosmic egg is unstable and would collapse. The inflating multiverse is caught by the boundary theorem. He summarized the situation in a single sentence. We have no viable models of an eternal universe. This is the crux, so let me be precise and let me be fair, because fairness is the whole strength of the case. Vilenkin is not a theist. He does not believe the theorem points to a creator. He believes the universe began through a quantum event he describes as creation from nothing, and he holds that no cause is needed. His co-author, Alan Guth, disagrees even with the conclusion, and suspects the universe may be eternal after all. The theorem itself is neutral. It does not mention God. What it does, with rigor, is remove a particular escape hatch. It says that the dream of a beginningless, eternally cycling cosmos, the dream the recurrence argument needs in order to deliver your return, is not supported by our best physics. As Vilenkin put it in his book, with a colon and a flat finality, there is no escape. They have to face the problem of a cosmic beginning. What does it mean that the scientists who proved time has a beginning are themselves reluctant to say so? It means the conclusion was not motivated, it was forced. And a forced conclusion, drawn against the inclinations of the people who proved it, is the most trustworthy kind there is. It is worth pausing here on the one cyclic model bold enough to claim direct evidence, because its fate is instructive. Roger Penrose argued that his endless eons should leave visible scars in the cosmic microwave background, the relic light of the early universe. Concentric circles of unusually low temperature variation, and warm patches he named Hawking points, the evaporated remains of supermassive black holes from the previous eon. In 2010, and again in 2018, Penrose and his collaborators announced they had found these patterns in the data from the WMAP and Planck satellites. It was a genuine, falsifiable prediction, and that is to Penrose's credit. He staked his model on the sky. But within months, 3 independent teams re-examined the claim and converged on the same flaw. The apparent significance had been computed by comparing the data against the wrong baseline, a featureless, random sky, rather than against the correlated, structured pattern that standard cosmology actually predicts. When the comparison was done correctly, the circles appeared exactly as often as ordinary chance in a perfectly standard universe would produce them. By 2024, careful reanalyses of both Planck and WMAP found no statistically significant circles and no significant evidence for Hawking points. The boldest observational claim of cyclic cosmology dissolved, under honest statistics, into noise. This does not prove the model false, but it means that, as of now, the eternal eons have left no fingerprint on the sky that survives scrutiny. So the first pillar falls. The universe is not the closed, finite box the theorem requires, and it has not run for the infinite time the recurrence needs, and it cannot have. Even the cyclic models, the most sophisticated attempts to manufacture eternity, are blocked from within physics by the entropy problem that Tolman found and the boundary that Borde, Guth, and Vilenkin proved. The eternal cosmos that would guarantee your return appears, on the evidence, not to exist. But suppose we grant it anyway. Suppose, for the sake of the strongest possible version of the argument, that time is somehow infinite, that the box somehow closes. Does it then follow that you, specifically, must recur? The recurrence argument leans here on an intuition that sounds unanswerable. Given enough time, anything that can happen will happen. Given infinity, everything occurs and recurs without limit. It feels like a law. It is, in fact, a fallacy. Here is the flaw stated plainly. The principle that anything possible must eventually happen is true only under a specific mathematical condition: that each possibility has a probability bounded above zero, and that the trials are genuinely independent and infinite in number. Strip away that condition, and the principle is simply false. Events of probability zero need not ever occur, even in infinite time. And more deeply, some outcomes are not a matter of waiting at all. They require a cause, a mechanism, a specific configuration that time alone does not supply. To say that infinite time produces all possible arrangements is to assume, without proof, that every arrangement is the kind of thing that arises by undirected shuffling. That is not a result of the mathematics. It is a metaphysical assumption smuggled in beneath it. Think about what the recurrence argument actually requires. It requires not just time, but a finite, well-defined set of states, and a low entropy starting condition that the system can return toward. In other words, the argument that you arose and will recur by the blind shuffling of an eternal cosmos already assumes the existence of the very thing most in need of explanation, an ordered, finely specified initial state, and a fixed set, laws that shuffle it. Time does not create those. Time spends them. We will come back to that ordered beginning because it is the heart of the matter. And there is a sharper problem still, one that infects the multiverse version of the argument from the inside. It is called the measure problem, and the physicists who work on eternal inflation regard it, candidly, as unsolved. Here is the difficulty. In an infinite multiverse, every possible event happens not once, but infinitely many times. There are infinitely many copies of you who make one choice, and infinitely many who make the other. To speak of the probability of anything, you must compare these infinities. And comparing infinities depends entirely on the order in which you count them. Alan Guth illustrated it with what he called the problem of the two-headed cows. In an infinitely branching multiverse, he noted, there are an infinite number of one-headed cows and an infinite number of two-headed cows. What then happens to the ratio? The answer is that it has no definite value. It depends on how you slice the infinity. Different slicing schemes give wildly different answers, and no one has found a principled reason to prefer one over another. What does it mean that the multiverse, invoked to explain why our universe is the way it is, cannot even assign a meaningful probability to anything? It means the theory, in this regard, predicts nothing. And a framework that can be made to predict anything, depending on how you count, has, in the words of one of inflation's own architects, zero power. The infinite cosmos that was supposed to make your recurrence certain cannot even tell you whether a recurrence is likely, because in it, the very notion of likely has come apart. Now we walk back through that door we left open, the door marked fluctuation. Recall that to rescue recurrence in an accelerating universe, the proponents had to say that you would reassemble as a spontaneous thermal fluctuation out of the equilibrium void. Let us take that seriously, more seriously than they may want, and follow it to its end. If the universe is an eternal system in which conscious observers arise as random fluctuations, then we can ask which fluctuations are most common. And the answer is devastating. Smaller fluctuations are exponentially, overwhelmingly more probable than larger ones. A fluctuation that produces an entire orderly universe with billions of years of consistent history is fantastically less likely than a fluctuation that produces the bare minimum required for a single moment of experience. And the bare minimum is not a cosmos. It is not a planet. It is not even a body. It is a single brain, flickering into existence for an instant out of the chaos, complete with a full set of false memories of a past that never happened, and then dissolving back into the void. Physicists call this a Boltzmann brain, after the same Ludwig Boltzmann, whose fluctuation hypothesis began the whole line of thought. The logic is merciless. In any eternal, fluctuating cosmos, these freak observers, these momentary brains with fabricated memories, would outnumber genuine, embodied observers like us by a margin as vast as the recurrence numbers themselves. Which means that if such a cosmos is real, then you, statistically, are almost certainly one of them. Your memory of starting this video, your sense of a coherent life and a solid world would be the fabricated content of a fluctuation that will vanish in an instant. The eternal cosmos that promised you immortality through recurrence instead predicts, far more strongly, that you are a delusion about to evaporate. Now, here is the move that turns this from a curiosity into a refutation, and it comes from the physicist Sean Carroll. A theory that predicts you are almost certainly a Boltzmann brain is not merely unsettling. It is, in Carroll's precise phrase, cognitively unstable. It cannot simultaneously be true and be justifiably believed. For if you are a randomly fluctuated brain, then the reasoning you used to arrive at that conclusion, your knowledge of physics, your trust in your own memory and logic, is itself just part of the fluctuation, with no connection to any reality. The theory, if believed, destroys the very grounds for believing it. It saws off the branch it is sitting on. And so, Carroll argues, the rational response is not to accept it, but to reject any cosmological model that predicts a cosmos dominated by such
fluctuations, not because we have measured it to be false, but because it is self-undermining and therefore unworthy of belief. What does it mean that the eternal, fluctuating universe required to guarantee your recurrence also predicts that your mind is a momentary accident with no access to truth? It means the picture refutes itself. You cannot use your reason to conclude that your reason is meaningless. The very act of following this argument is evidence against the cosmos the argument describes. The eternal return, pushed to its honest conclusion, does not give you 1,000 lives. It dissolves the self that was supposed to live them, and then dissolves the trust in reason that was supposed to prove it. So, 3 pillars have now fallen. The universe is not the closed box recurrence requires. It has not run and cannot run for the infinite past the recurrence needs. And even granting infinite time, the claim that everything recurs by chance is either a probability fallacy or it collapses into a self-refuting cosmos of Boltzmann brains. The grand structure of eternal return, examined honestly, does not stand. But knocking down a structure is only half the work. The deeper question is what stands in its place. For there remains, untouched by all of this, one stubborn fact. The fact that every cyclic model and every recurrence argument quietly assumed and never explained. The beginning was ordered. And we must now ask what that order means. Return to the one fact that survived every demolition. Whatever model you choose, the cyclic cosmos, the multiverse, the single Big Bang, the recurrence argument needed the universe to begin, or to begin each cycle, in a state of extraordinarily low entropy. A smooth, ordered, finely specified starting condition. Without it, there is no arrow of time, no second law, no structure, and nothing to recur. The eternal return picture treats this ordered beginning as a free gift, a given, the floor it stands on. But the flaw is the entire question. How ordered was the beginning? Roger Penrose, the same physicist behind conformal cyclic cosmology, calculated it. And the number he arrived at is, in my judgment, the single most staggering figure in all of science. For the universe to begin in a state as ordered as ours, Penrose found, a creator selecting it from the space of all possible universes would have to hit a target of 1 part in 10 to the power of 10 to the power of 123. Let that structure register. Not 1 in 10 to the 123, 1 in 10 raised to the power of a number that is itself 1 followed by 123 zeros. Penrose remarked that you could not write the number out in full, because even if you placed a single zero on every particle in the observable universe, you would run out of particles long before you ran out of zeros. Now, hold that beside the recurrence argument and see the sleight of hand. The argument says, given an ordered, low-entropy, finite, lawful system and infinite time, you will recur. But it never asks where the order, the low entropy, the finiteness, or the laws came from. It assumes the most improbable thing in existence, a beginning fine-tuned to 1 part in 10 to the 10 to the 123, and then acts as if the only mystery left is the passage of time. Time does not produce that precision. Time degrades it. Every moment, the second law spends that initial order down toward disorder. The ordered beginning is not explained by eternity. It is presupposed by it. Consider a combination lock, but a strange one. It has not 3 dials, but a number of dials beyond counting. And each dial must be set not merely close, but to one exact value. And only then does a universe capable of stars, chemistry, memory, and thought swing open. Set the dials at random, and you get no stars, no atoms, no structure, nothing that could ever recur into a self. The recurrence theorist hands you the lock already open, already set to its one life-permitting combination, and asks you to marvel only at the fact that, given enough time, the open lock will be found open again. But the miracle was never the recurrence. The miracle was the setting of the dials. And dials that are set to one precise configuration out of a space of unthinkable alternatives, are not the signature of accident. A specific selection out of countless possibilities is the signature of a choice. And a choice requires something that can choose. Picture an investigator who walks into a room and finds, laid out across a long table, 10,000 dice, every single one showing a 6. She has 2 explanations available. The first is that the dice fell that way by chance. She can calculate the odds, and they are so small that to write the number down would take longer than the history she is investigating. The second is that someone arranged them. No law of physics is violated by the chance hypothesis. It is merely, overwhelmingly, not how a rational person reasons. She infers an arranger, not because she has seen one, but because deliberate arrangement is simply what the evidence is. Now multiply the dice beyond counting and make each one not a choice among 6 faces, but a choice along a continuous dial, and make the consequence of the setting not a pattern on a table, but the difference between a universe of stars, chemistry, and minds, and a universe of formless, sterile chaos. The low entropy beginning is that table. The recurrence argument asks us to stare at the perfectly arranged dice and to marvel only at the thought that, given eternity, they might one day be found arranged again. It never asks who set them the first time. This is the part that I keep returning to. When I first followed this chain to its end, the materialist account I had quietly assumed began to come apart in my hands. Not because the physics was wrong, the physics is magnificent, but because the physics kept handing me, at every step, a precondition it could not itself supply. The laws, the constants, the bounded lawful order, the improbable, pristine, low entropy dawn. These are not the conclusions of the cosmic story. They are its opening sentence. And an opening sentence is written before the story begins to run, by something that is not itself a character in the story. This is where the prosecution rests its positive case. And it does not rest on ignorance. It does not say, we cannot explain the ordered beginning, therefore a creator. It says something stronger. It says that the structure of the explanation itself, an improbable, precise, specified initial condition, fixed laws, a bounded and lawful system, points toward exactly the kind of cause the evidence has been describing all along. Something that existed independent of the universe it configured. Something not bound by the time that began with that universe, and therefore eternal and uncaused. Something with the knowledge to specify a state of such precision and the will to select it from the alternatives. Power, knowledge, and will. These are not the properties of unconscious matter, which has no preferences and makes no selections. They are the properties of a mind. And now, the boundary theorem and the ancient argument meet and reinforce each other. We saw that the Borde-Guth-Vilenkin theorem forbids the eternal past, the cyclic models needed. The universe, or the chain of cycles, must have a beginning. But this is precisely what philosophers argued long before the physics existed, on grounds of pure logic. An actually infinite chain of completed past events cannot exist, because to arrive at the present, the entire infinite series would have to have been traversed, completed, finished. And an infinite series, by its nature, can never be completed. You cannot count down from infinity and reach zero. Whatever exists now is reached by a finite chain of causes, and that chain must terminate in a first member that is itself uncaused, something that did not begin, something that does not depend on anything prior. The physics, arriving by an entirely different road, the kinematics of expanding space-time, reaches the same destination the logic reached. The chain of dependent causes is not infinite. It terminates. It began. What does it mean that two completely independent lines of reasoning, a 21st century theorem in general relativity and a centuries-old argument in metaphysics, converge on the identical conclusion? It means the conclusion is robust. When the mathematics and the logic, starting from different premises and using different tools, arrive at the same place, that place deserves to be taken seriously. The honest objection at this point is the one that has been offered for a century. We do not know yet, but science will eventually explain the ordered beginning without invoking any cause beyond physics. And this deserves a fair answer rather than a dismissal. The answer is that this is not an argument. It is a promissory note, a faith in future discoveries that may never arrive. And more importantly, it misunderstands the kind of question being asked. Science describes how the universe operates, how the dials, once set, govern the unfolding of stars and time. It is extraordinarily good at this. But the question of why there is an ordered, lawful, finely specified universe at all, rather than nothing, or rather than formless chaos, is not a question about how the machinery runs. It is a question about why there is machinery, and why it was set as it was. That is not a gap in our current physics that better physics will fill. It is a different kind of question, and the recurrence argument, for all its mathematical grandeur, never even reaches it. It assumes the answer and studies the leftovers. There remains the most intimate question, the one the title pressed from the start. Even if, somehow, against all of this, a configuration identical to you were to occur again, would it be you? Here, the materialist picture that underwrites the whole fantasy of recurrence turns on itself one last time. If you are nothing but an arrangement of particles, then two things follow, and both are fatal to the comfort the idea seems to offer. First, a duplicate is a duplicate, not a continuation. A perfect copy of a configuration, assembled trillions of years or an infinity of space away, is, by every ordinary standard, a numerically distinct individual. It would wake into its life believing itself to be the original, exactly as you believe yourself to be you. And it would be wrong in the same way, or right in the same way. But it would not be the carrying forward of your consciousness. You would still have ended. Someone exactly like you would begin, unaware. The recurrence does not save you. It replaces you, and tells the replacement it is you. Second, recall what the physics already established. A recurred copy could carry no memory across the gulf, because memory is a record, and records are made by increasing entropy, and the high entropy wall between one ordered state and its return erases every ledger. So even on its own terms, the eternal return offers not a remembered immortality, but an infinity of first times, each one ignorant of all the others, which is to say, no continuity of self at all. The self that the recurrence was supposed to grant eternal life is precisely the thing the recurrence cannot preserve. And so, the materialist who reaches for recurrence as a substitute for the soul ends in a strange place. To make the recurrence meaningful, that there is a real you who genuinely lives again, you need exactly what materialism denies: a self that is more than its momentary arrangement, a continuity that persists through and beyond the configuration of particles. You need, in a word, the very thing the whole framework was built to do without. The longing that makes eternal return feel like hope, the longing not to be extinguished, is itself evidence of something in us that resists being reduced to a pattern that merely happens to repeat. We do not merely want the pattern to recur, we want to continue. And a being that can want to continue, that can be aware of its own existence and grieve its ending and ask whether it will return, is not the kind of thing that unconscious matter, however cleverly arranged, has ever been shown to produce. This is the part that stays with me. Not the size of the recurrence numbers, though they are vast beyond holding. It is the quiet reversal at the center of the whole subject. We began with a theorem that seemed to promise the universe could give us eternity for free by sheer repetition, with no need for anything beyond matter and time. And, following it honestly, step by step, we found that it cannot deliver eternity, because the universe is not the closed eternal box it would require. We found that even if it could, it would not deliver you, but a stranger wearing your face. And we found that the one thing it could never explain, the ordered beginning it depended on entirely, points past matter and time altogether, to a cause that chose. Let me bring this exploration to a close. We began with a demon's question, asked in the loneliest hour. Would you live this exact life again, infinitely, unchanged? We followed it into the mathematics of Henri Poincaré, who proved that a finite, closed system in eternal time must return to its beginning, arbitrarily closely, forever. We watched that theorem grow from a cubic centimeter of gas into a claim about the cosmos, carried there by the cyclic universe models of Tolman, of Steinhardt and Turok, of Penrose, and by the eternal inflation of the multiverse. We confronted recurrence times so vast, the age of the universe rounds to nothing beside them. And then we tested the foundations and watched them give way. The universe is not the closed box the theorem requires. It is accelerating into cold dispersion. It has not run for the infinite past the recurrence needs. The Borde-Guth-Vilenkin theorem, proved by men who wanted no part of this conclusion, says it began. We watched the Ergodic Assumption falter, the quantum recurrence fail for a dispersing cosmos, and Penrose's circles in the sky dissolve into noise, leaving the boldest evidence for an eternal cosmos unsupported. The promise that infinite time makes all things recur is a probability fallacy, and where it is not, it dissolves into a self-refuting cosmos of fluctuated minds. What remains when the eternal machinery is cleared away is a single, stubborn, luminous fact. The universe began, and it began in a state of order so precise that no accident in the language of mathematics can name its improbability. Precision of that kind is not the residue of endless shuffling. It is the mark of a selection, and a selection is the act of a will. The evidence does not point to a cosmos that grants its own eternity through blind repetition. It points to a beginning, and behind the beginning, to a cause that is itself uncaused, eternal, possessing the knowledge to specify such a state and the will to choose it. not unconscious matter, an intelligent cause. You will not live this exact life again by the mercy of an eternal machine, because there is no eternal machine. There was a beginning, and a beginning is the fingerprint of the one who began it. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. The demon asked whether you could bear to live your life again, unchanged forever. But the deeper truth is gentler and stranger than the demon knew. You were not flung up by an eternal accident, doomed to repeat. You were begun, once, on purpose, by something that chose for there to be a you at all. Rest tonight, not in the cold comfort of endless repetition, but in the stranger thought that your single, unrepeatable life was not an accident the cosmos stumbled into, but a thing that was, in the most literal sense, meant. Good night.